Hello everyone, I'm Cedric from MDPI and I will be your host for today. Welcome to the first live session of the second International Electronic Conference on Plant Sciences, IECPS 2021. This e-conference is hosted online from the 1st to the 15th of December 2021 and is organized by MDPI and the journal Plants. During this time, the conference presentations will be available for discussion on the conference's website. The accepted proceedings papers will be published in the Biology and Life Sciences Forum journal, and selected papers will be considered for publication in a special issue of the journal Plants. I would like to thank the conference chair, Professor Adriano Sofo, the conference committee, and the session chairs for making this e-conference possible, along with the speakers and, of course, our attendees. I would like to remind everyone that this is being recorded and the recording will be made available as soon as possible on the webinar's webpage. Please note that you will have to be logged into SciForum in order to view the recording. Today's session is also being live streamed on MDPI's YouTube channel, so hello to those of you watching us on there. There will be two presentations today of 20 minutes each. The presentations are followed by a short question time moderated by the chair. If you have any questions for our speakers, please feel free to post them in the Q&A box. You can do it by clicking on the Q&A option in the Zoom menu bar at the bottom of the screen. Please remember to add the name of the person to whom you're addressing your question. Thank you. Today's live session is chaired by our conference chair, Professor Dr. Adriano Sofo. Professor Sofo is currently an associate professor of agricultural chemistry and plant biology at the University of Basilicata in Matera, Italy. His research fields are physiological and biochemical response of plants to stresses, soil chemistry / microbiology and soil sustainable management, and last but not least, food quality and plant secondary metabolites. He is an author of over 150 papers published in peer-reviewed journals and books, editor-in-chief of the International Journal of Plant Biology, and section editor-in-chief of the MDPI journal Plants. Recently, he was listed among the 2% of the most cited scientists in the world in 2019 and among the top Italian scientists in the macro area of natural and environmental sciences. Thank you to Adriano for chairing this session. I now hand over the mic to you, and I hope you enjoy, everyone. Thank you.
Thank you, Cedric. And this is the first live session of the conference. So good morning to all the participants to this second electronic conference on plant sciences. And I hope you are safe and healthy in this period. And just a short introduction of the conference, as is the first live session. It's a great pleasure to welcome you to this conference, where I'm honored to be the chair. And this conference is about plants. And from a human perspective, plants are sessile, blind, deaf, living organisms, and may look solitary individuals. And often we forget that life on Earth depends almost entirely on these complex organisms. Starting from this statement, this conference is aimed to deep plant research at all levels, from the molecular through the whole plant and community scale, also including bioinformatics and modeling approaches. This year, we are particularly highlighting the importance of contributions to current topics such as plant-plant communication, protection of plant biodiversity, and plants in urban environments. And for this purpose, the conference is organized in 6 focused sessions. IECPS 2021 is an online-only proceeding, which allows participation from all over the world with no requirements for travel or related expenditures. This electronic conference organized by MDPI provides a platform for rapid and direct exchanges about the latest research findings and novel ideas. And at this stage, I thank the authors of the submitted contributions to this scientific event for their active support and fundamental support. And finally, I would really like to thank MDPI Conference Secretariat, particularly Cedric and Mr. Leo Zhu and Mrs. Stephanie Lee, who helped me continuously during all the stages of the organization of this conference. In the live session of today, I'm glad and honored to introduce two speakers. The first one is Professor Dr. Hazem Kalaji, that we talk about communication with plants using chlorophyll fluorescence signals. Professor Kalaji is a professor at Warsaw University of Life Sciences in Poland. He is a director for research and technical development, SI Technology in Poland, European Commission Vice Chair of the Scientific Committee, MSCA, Assessor of HR Excellence in Research Award Evaluation, member of UK Controlled Environment Users Group in UK, and member of the Science Advisory Board, US. He is also scientific consultant and advisor in Central and Eastern Europe and Middle East. The main topic of Professor Kalaji is photosynthesis, and we know that photosynthesis is the most important process on Earth, not only for plants, but for all living organisms. And understanding the nature of this process is crucial, and we know that many methods have been used at different structural, functional, and spatial levels to better understand the mechanisms that determine the performance of photosynthetic apparatus, especially under unfavorable growth conditions. Currently, chlorophyll fluorescence measurement is considered to be one of the most prevalent tools used in this area, and Professor Kalaji will talk about this important topic. The second speaker is Dr. Ludovica Lela, with a talk titled "To Make the Best the Bitter, Health Promoting Phytochemicals from Humulus lupulus as Oxidative Stress Remedy." Dr. Ludovica Lela obtained her master's degree in pharmacy in 2020 at Christian Albrechts University in Kiel, Germany. Currently, she is a PhD student at University of Basilicata, the same university where I work. The main field of her research deals with studies on biological active extracts obtained from medicinal plants, as well as phytochemical characterization of specialized metabolites responsible for their activity. We know that this topic is very, very important nowadays, because for centuries, natural medicines have represented the only option for treating human diseases. And nowadays, plant phytochemicals can be considered as promising compounds to treat or prevent chronic conditions. And among them, hop flowers, Humulus lupulus, the object of this talk, is typically used in brewing industries to give the typical aroma and flavor to beer. And they have attracted particular attention for their health promoting properties. And these phytochemical activities, suggest a possible role of bitter hop acid in preventing metabolic syndrome and its related diseases. So I'm very glad to host these speakers, and I think that this is the time for Professor Hazem Kalaji. Professor Kalaji, the floor is yours, so you're welcome to present your presentation. Thank you.
Thank you very much. Good morning, everyone. Good day for the others who have already the evening time, because I can see that we have participants from different places in the world. Okay, so first of all, I would like to thank the organizers and the people who are behind this conference. Thank you for this opportunity. I hope that I will be able to extend some new knowledge for some of you, and maybe I will remind the other type of the knowledge for the others who are very well experienced in the same field of photosynthesis. So my talk or my speech is related about the way, a new way, which we can communicate with the plants using the process of photosynthesis. And the presentation was created by me and other two friends from Poland, Dr. Dąbrowski and Dr. Aneta Haczewska-Dąbrowska. From the abstract, you can see that the presentation is addressed to talk about the use of the plants as a bioindicator, as biological feedback system, which can allow us to control, allow the plants to control their environments in the future by the use of deep learning and the artificial intelligence. And I will explain how we can do that. So we know that in our nature, in our life, in the surrounder, we have different type of living organisms, and all of them, they are in communication in different ways. We are interested about the communication with the plants which, in my opinion, are the most intelligent living organism on Earth. Why? Because they have to survive. This is the only living organisms which is standing in the nature. So nevertheless, of the type of the stressor that they are dealing with, is it in the soil or in the air, is it too high light or too temperature, low temperature, whatever, they have to stick in the soil and they have to survive. What that means? They survived already for thousands of years or more than that. We are not sure about the first date of their existence on Earth. However, we know that during the evolution, they proved they can exist. It doesn't matter, or nevertheless, of the external environments. That means they have the most advanced mechanisms and strategies for living and existence, more than the people, because if we feel something bad, we can run the AC or put some coats. If there is a low temperature, we can put an umbrella. If we have the rain, the animals can hide in the caves or somewhere under the trees, but the plants, we cannot do such things, so they have to stand. That means they possess the most powerful mechanisms to allow them to do that. And this is why we decided many years ago to go inside these mechanisms to understand how they survive such type of stressors. So it's already known from the literature that plants, they do communication with the surrounder, with the insects, with the animals, with the people as well, but we still don't recognize their signals. And what we need is to get or to build up a tool which allow us as well to hear their talk, because they are talking, and to have a good communications with them. So it's as Professor Adriano said, photosynthesis is one of the most, I believe this is the most important physiological process on Earth. It's not because only the tight correlation between the human being or other living organisms and the plants, because this correlation is close, as you can see. So once we are breathing, we are getting the carbon dioxide, which they are using in photosynthesis. On the other side, they are giving the oxygen, which we are breathing. So it's a very tight correlation, but it's not only about this tight correlation why this process is important. We found during our research that this process is a mirror of what's going on in the other metabolic pathways in the cells. This is already proved. So we found two facts. The first one, that photosynthesis is the most sensitive process in the plant cells. The other things which we found, that it's related and connected with all other as you can see here, metabolic pathways in the cell. What that mean? That means we can use this process as a mirror of what's going on in the cells, in the living organisms and the plants, to see what is the physiological status of them. And this was the aim of our research, let's say more than 20 years ago. We start to concentrate on this process. So not just to remind you something, because not many scientists even know these facts, that from this coming energy, from the light, could be ambient light, artificial light, it could be the sun or the artificial one, LEDs or lamps, whatever. The plants, they use only a small part of this light energy in photosynthesis. So what is about the biggest part of this absorbed light energy? It's already proved that the plants, they are, well, we say that they are losing, but actually it's a mechanisms controlled by the plants for survival. So the things, it's a matter of point of view. We believe that this is a lost energy, but they don't do the same. They don't think the same. So the big part of the energy is lost as a heat, and the small part which we are interested in is about 3 to 5% is emitted from the plants as chlorophyll fluorescence. So why we concentrated on measuring these signals? Because these signals, as you can see here, are a part of a closed mathematical formula. So if we look for the whole energy captured by the plants at 100%, so we have 3 parts: photosynthesis, which I said is about maybe 10%, then the chlorophyll fluorescence, which is about 3 to 5%, and 90%, sorry for that. So, okay, 90%, which is heat dissipation. It's lost, it's emitted as heat dissipation. So once you measure the chlorophyll fluorescence and heat dissipation measurements, then you will learn about photosynthesis. It's something about what you are looking to the part which is not used in photosynthesis. So any changes in these signals here, which we are measuring in non-invasive way, in very fast way, in 1 second, we can learn about the physiological status, which is mirrored, which is expressed, as I said, by the process of photosynthesis, which is the most, against saying that the most sensitive process in the plant cells. So it's already found by Professor Kautsky in the last century, in 1973, that once you the photosynthesis value will go up, the signal of fluorescence will go down. And we are using these facts nowadays to learn about the physiological status of our plants. So, just to put the things in a simple way, if we would like to check if a man or a woman ill or not, you give a bottle of water, and we know that the healthy people will drink more water than the ill people. So we do the same with the plants. We give them a big dose of the light energy, and we see how much of this light portion they will use in the process of photosynthesis. So instead of doing plant gas exchange measurements by measuring the photosynthesis intensity and transpiration and other gas exchange measurements parameters, we do in 1 second measuring the rest of the not used energy by the plants. So if you look how much left in the bottle, you know how much, okay, these women drank. And this is the trick by doing these type of measurements. So we found that analyzing the activity and the efficiency of photosystem to the enzyme, which is responsible for converting the light energy to biochemical energy, is very comparable to the heartbeat of the people. we have a fixed value from parameters which we call it a VFM, which is about 0.83, 0.85 in the nature. Whenever you have any objects, plants, photosynthesizing organisms, could be algae, mosses, lichens, whatever, it should show the same. It doesn't matter it's growing in Italy or in Poland or in China or in India. You have a fixed value for any plants on Earth. The same, we have very similar analogical situation with the people. It doesn't matter about the nationality. You have 60 to 90, it's not 80, pulses or bites per minute. This is showing the activity of the heart. So we start to call this enzyme, the photosystem 2, is the heart of the plant. Why? More reasons. Because by stethoscope, which is a very simple tool used by any doctor around the world, and this is the first things which they do with us whenever we feel bad. We go to the internist, and the internist is measuring the heartbeat of the people. So we do the same by chlorophyll fluorescence measurements here by fluorimeters. We do measurements in 1 second, and we learn about the physiological status of these plants. More advanced research, the doctors, medical doctors, they are doing with us, they are doing electrocardiographic curves, and we do the same by advanced fluorimeters with the chlorophyll fluorescence measurements. So this is the signal of the heartbeat of the plant of the people, and this is the signals which we are getting from the plants. And it's, believe me, it's the same or almost similar analysis of these signals. So the distance between the peaks, it has its own physiological meaning, and the height of these peaks has again its physiological meaning. So we started to recommend this technology of these devices, which are usually measuring this chlorophyll fluorescence, to be applied everywhere. Everywhere, whenever you have chlorophyll in the oceans, in the river, for pollutions, in the space, whenever it's possible, in the greenhouses, in the field, to use this method. And we indicated that this is a very good bioindicators and biomarker methods because it's sensitive, reliable, and non-invasive and fast. In 1 second, I will show it later to you. We have more than 100 points on the induction curve. So it's applicable at different organizational levels and at different time as well levels. We can start by searching changes at the level of the cells, ending with the ecosystems. So we have usually already known 2 types of these technologies. One of them is continuous excitation fluorescence measurement system, and the second one is pulse modulated. They are not the same, they are complementary. There is 2 schools on the world doing this type of measurements. I'm one of the very rare people who advocates and trying to convince the people that both of them should be applied to get better information from the plants. You can see that these fluorimeters are really portable devices. You can have them on your neck, and you go in the field and you can collect thousands of information per day from your plants. So using this first type of technology, which is the fast excitations, you can have a lot of information about the physiological status of the plants based on the photosynthesis, photosynthetic efficiency, very similar or let's say similar signals, but showing the actual activity of the plants can be obtained if you will use the other type of the technologies. So once you apply this type of measurements, you will have a curves like this one, which consists 116 points in 1 second. This is what we need now for calibration the systems and for building, a system which allow us to hear the plant talk. And we already proved, many of people, thousands of papers, that each changes here in this curve, this is optimal curve, will be correlated to a specific physiological process in the whole chain where the energy, the light energy, is converted to biochemical energy. You can see here as well that depending on the stressor, the shape of these chlorophyll fluorescence signals will be different. So this is the optimum, which we will have it for any living organisms in the world. And when you apply, for example, high temperature, you can see the changes which is affecting only these two phases. Different type of stressors, different type of reactions. This what allowed me a few years ago to start to see, okay, so I have a specific changes on this curve, which allow me maybe to identify a specific stressor. So it's a matter of, machine learning and application of the artificial neural networks can allow us to do that. So because we have a 1 second measurements, usually we do at least 30 measurements for each treatment, for each experimental variant. Here is the optimum, here is the magnesium deficiency, and the necrotics. So because we have more than 75 calculated parameters, more than 116 points on the 1 second conduction curve, we can really have a very potential tool which could be applied, to build up a system which allow us to communicate with the plants. So we started a few years ago, by the application of the basic of the informatics. What if, the basics is the tool is very simple. So what if this value and this value will be among this amount, and the other one will be bigger than this, the other one will be that. Then it will be indicated of water stress. The other one will be nitrogen deficiency, low temperature, whatever. Then if you will feed back this black box, which we have it at the beginning, as an empty box of information, then we can put the things on the opposite sides by building this biological feedback system that the plants by themselves, they can tell us, they can talk what is the type of stressors which they are dealing with. It's possible. We already have some steps on this road. It's a long road. It's a very far horizon of our work and researches, but we already tried to do it. This is the first prototype worldwide which we built. We have ability to get information from the plants about the light needs, and we put it on the other way that these plants here is available to control the light intensity which is coming from here, from the LEDs, as the plant's wishes, not as the end user wishes. So it's providing the light intensity to the level that they have the best photosynthesis, the optimal photosynthesis process based on the measuring the chlorophyll fluorescence measurements. And this is the scheme, well, simplified scheme of these systems. So first you teach the system, then you allow the plants to control the environments by themselves. This is what it looks like now. The camera, it's a monitoring camera which was modified by me, and we built in a fluorimeters here, you can see, with a blue laser beam, and this camera allow us to have, a view of what's going on in the greenhouse, and live signals coming from the plants showing their physiological status. So the first step already done. And what we have is live signals coming from the plants. So we start to hear the plant talk based on the most important photosynthesis on Earth, which is photosynthesis. We already know, some of you already heard that something similar already was done by scientists based on the electrical signals, but we still believe that electrical signals could be fragile, yes, sensitive, but they could be affected by other factors. Photosynthesis is the most pure sensitive, I think, physiological process which really we can trust. Yeah. So this is an invitation for anyone who is interested in building such a system with us for cooperation. As we said, the road is very still long and far away. The aim, the milestones are coming one by one. And I believe that this will be a revolution, especially if we are thinking about saving the energy in the greenhouse. So imagine that the plants in the greenhouse, they will control the light intensity and quality and temperature and humidity, the doses of the fertilizers as well, if they will have, you know, these such biological feedback systems. So the user, us, as we are doing now, we are giving everything with an extra, you know, spare amount. And this is just causing, you know, a big cost of fees and charges for any plant production. Thank you very much.
Thank you, Professor Kalaji. Thank you for your talk, very interesting, and I have many questions, but we will do it at the end of the presentations. And now is the turn of Ludovica Lela, Dr. Ludovica Lela, and the floor is yours, Ludovica, please.
Thank you. I'm so glad to be here, and thank you, Professor Sofo, for the presentation. Today, I am going to present our work on open fluorescences as a potential remedy in oxidative stress. But firstly, what are natural products? Are compounds produced by living organisms. In recent years, they became the center of attention of scientific community because of its widely application in different fields, in particular in pharmacological one. In fact, in the last 20 years, there was a rapid multiplication of various databases reporting information about them. We know that resveratrol is really known since ancient time and is the polyphenolic compound of Vitis vinifera. It was the protagonist of the French paradox in 1992 because it was observed that in French people, despite their high consumption of food rich in saturated fatty acid, the incidence of mortality was relatively low. And it was observed that this compound was responsible of a protective effect on blood vessels and also antioxidant and anti-inflammatory activities. Another well-known molecule, really known since times, is curcumin, which is extracted by the root of Curcuma longa. Curcumin was used in the past for dyeing the fabrics, and today is curcuma is used in is a food ingredient, and curcumin is reported for its antioxidant activity, in particular for the upregulation of superoxide dismutase and glutathione peroxidase, which are involved in antioxidant defense. But in the last decades, also bitter principles became really interesting. In particular, amarogentin is maybe the most known bitter principle extracted by the root of Gentiana lutea. In Italy, he's used this plant for the liquor of Gentiana, typical of different Italian regions. But also amarogentin in particular was effective as an anti-cancer and anti-infective agent. Among the plants with high content of bitter principles, we can mention Humulus lupulus, which is a perennial plant belonging to the family of Cannabaceae. Humulus lupulus occurs generally in temperate regions of Asia, Europe, and North America, and it can reach 10 meters in height. The Latin word lumulus means little wolf because of its struggling habits on the other plant. The most studied part of the plant are represented by the female inflorescences, also known as hope inflorescences, as reported in the figure, that are rich of resinous glands which secrete a yellow substance called lupulin, where the most of the bioactive compounds are synthesized, like alpha and beta acids, polyphenols, prenulated flavonoids. All we know that Humulus lupulus is used as food in food industry for the is the ingredient of the beer, because of thanks to its bitter principles is responsible of the bitter flavor of the beer. In particular, the responsible compounds are represented by iso-alpha acids that are originated by alpha acids for isomerization during brewing processes. In addition, it is important because it can increase the preservation and conservation of the beer thanks to its phytochemical composition. It is also used as a cosmetic ingredient in bath lotions or shampoo for its antifungal and anti-seborrheic effect, and it also reduces the loss of the hair. And then it is reported for its medical application as antimicrobial, anti-inflammatory, anti-cancer, and antioxidant. Among the antioxidant effect, we can mention different natural compounds, like, for example, plant polyphenols. These compounds can be divided into different classes based on their chemical structures. And they are really important in some pathological conditions like in oxidative stress. Generally, reactive oxygen species are produced by a physiological reaction of our cells, but sometimes when exposed to environmental stressors or UV or xenobiotics, there is an increase in their level that causes an imbalance between the antioxidant mechanism of our body and ROS level in a pathological condition known as oxidative stress. So plant polyphenols or natural compound can represent a good strategy to overcome this limitation. But despite their many health promoting effects, plant polyphenols have low solubility in water and they are unstable under certain conditions like pH, temperature, or gastric enzymes action. So nanoformulation can represent a good strategy to overcome their instability. For example, an application of a nanosuspension on piperin, which is the alkaloid of Piper nigrum, increase the oral bioavailability of it. Or gastro-resistant formulation can be used to overcome the gastric enzyme activity and increase the concentration of the extract or natural compound or drug in the intestinal tract. Or liposomes can represent a good alternative. They are vesicle particles that are made of phospholipidic molecules. With a polar head and hydrophobic tails. These structures is important because can entrap both hydrophilic or hydrophobic compounds. In addition, can improve the stability and bioavailability of compounds because they can control the release of the drug or the compound in a specific site or organs or tissues of our body. In addition, they can mask the amplesion test that in the case of Humulus lupulus is important to mask the bitter taste that can reduce patient compliance. So based on this introduction, the aim of our study was to evaluate the antioxidant activity of Humulus lupulus raw extract, but also after its incorporation into liposome vesicles. We started with an extraction made by hydroalcoholic maceration by using ethanol. And then we have done the phytochemical analysis by using HPLC-MS, which led us to the identification of 24 compounds by comparing the fragmentation pattern and retention time with literature data. In particular, the compounds identified are belonging to different classes like phenolic acids, and we have identified chlorogenic acid, or among the flavonoids, we have identified glucosides and aglycons flavonoids like quercetin, quercetin 4-diglucoside, rutin, isoquercetin, luteolin, luteoloside, and luteolin rutinoside. Among the bitter principles, we have found the alpha acid humulon, co-humulon, and ad-humulon, and the beta acid lupulon, lupulon E, lupulon C, and colupulon. While among the prenyl flavonoids, we have identified xanthomol, isoxanthomol, 6 or 8 prenyl naringenin, and 6 geranyl naringenin. Animated by the interesting phytochemical profile, we have evaluated the antioxidant activity by using 3 different but complementary assays. Our extract, in fact, showed a good radical scavenging activity against the cationic radical ABTS. In addition, it showed a good ferric ion reducing power evaluated by FRAP assay, better than that found in literature regarding a methanolic oat extract. And also the extract showed a good inhibition of radical peroxidation, lipidic peroxidation evaluated by beta-carotene bleaching assay. Then we have evaluated the antioxidant effect of extract in a cell model line. To this purpose, human hepatoma cell line were used as model cells because of their many features in common with human hepatocytes, and because they have more reproducibility than primary hepatocytes. Firstly, we have done a cytotoxic effect, a cytotoxic activity evaluated by MTT assay, which measured the conversion, the reduction of the yellow tetrazolium salt into purple formazan by the enzyme succinate dehydrogenase, which is a mitochondrial enzyme active only in viable cells. After the cytotoxic effect, we have evaluated the antioxidant activity by flow cytometry by using dichlorofluorescein assay. In particular, dichlorofluorescein D-state is a non-fluorescent probe that, when in cells, thanks to the activity of cellular esterase and for reaction with reactive oxygen species, originated the fluorescent probe dichlorofluorescein. So the fluorescence intensity is directly proportional to reactive oxygen species level. In particular, we have simulated a stressed environment by using the oxidant erzbutyl hydroperoxide. And we found that our extract in all the tested concentration reduced the fluorescence intensity in a dose-dependent manner. In particular, the highest doses showed a good antioxidant activity, better than the well-known antioxidant N-acetylcysteine. So we have evaluated the molecular pathway involved in antioxidant activity, and we found that the treatment with the OP extract for 24 hours increased the upregulation or induced the upregulation of the nuclear factor erythroid 2, which by linking the ERE sequence, it can upregulate superoxide dismutase and MADPH quinone oxidase, which are also involved in the antioxidant defense. In addition, the extract upregulated the expression of uncoupling protein 2, which is an important protein that reduces mitochondrial membrane potential and also create a dissipation of proton gradient, thus reducing ROS level. So our interesting results led us to introduce the extract into a vesicle formulation represented by liposomes. This was made in collaboration with Professor Carla Caddeo from University of Cagliari. Our vesicles with the extract were tested for the entrapment efficiency that was around 80%, and also for cellular uptake by measuring the amount of the bitter beta acid colupulon. And we found that in both the tested concentration, the extract introduced in liposome has a highest content of, amount of colupulon of around twofold in comparison with the raw extract. So we have evaluated the antioxidant activity of the extract entrapped in liposome in comparison with the raw extract, and by using also the flow cytometry assays with dichlorofluorocane. And we found that also when the extract was incorporated into liposome, showed a great antioxidant activity by reducing fluorescence intensity in all the tested concentration, especially at the lowest one, thus improving the antioxidant activity of the raw extract. In conclusion, the LCMS led us to the identification of different compounds belonging to different classes, including bitter acids and phenolic compounds. It was also demonstrated a protective effect against oxidative stress by using APG2 cell line as a model cell. And for the first time, Humulus lupulus extract was introduced in liposome vesicle, showing an improved activity. In the future, we will make a quantitative analysis of the compounds identified. We will, of course, evaluate the activity of the extract in other cell line, and in particular, we will evaluate the satiating activity in an intestinal cell line, because we know that bitter principles can link bitter taste receptors in the gastrointestinal tract and can increase the release of good hormones like glucagon-like peptide 1, cholecystokinin, or peptide YY, which are related with the satiating activity by acting also in central nervous system. And of course, we will confirm our result in vivo study. Here I have reported the table with all the identified compound and retention time and fragmentation pattern. Thank you for your attention.
Thank you, Dr. Lela, and thank you both for your very interesting presentations. And there is space for some questions. In the chat box, I can see a question for Dr. Lela. How did you estimate the IC50 value for antioxidant activity?
Yeah, we have used GraphPad software to estimate IC15, and after that we choose concentration under this value to evaluate the antioxidant activity, because the cells should be viable, so we use the concentration under this value.
Okay, so I have a question for Ludovica, Lela. And you have found many substances, many compounds, and from at the first glance, it seems that many of them have strong antioxidant capacity. And do you think that some of these compounds can be better than other ones? They can have maybe a higher antioxidant activity compared to other ones, if there is one in particular or two?
Yes, in general, for what is present in literature, flavonoids are the better compound for the antioxidant activity. It was reported also low antioxidant activity regarding the bitter principles, so the alpha and beta acids, but compared with the flavonoids, they are not really antioxidant. They can increase maybe the activity of the flavonoids, but they are not the only responsible.
Thank you. Thank you.
Thank you for your question.
And Professor Kalaji is here, and there is a question for you. And thank you for your speech. And as we are aware, in in-field measurement of yield and growth in the real world might be imprecise and costly, limiting its scientific and commercial application. In your point of view, on which aspect should we focus in the future research?
Yeah, thank you very much for this question. And well, I believe that I don't so to make a big, let's say, announcement, but you know, I have been dealing with the plants for 35 years now in my life, and I found really that a lot of things should be comprehensively, let's say, changed. We have to change our concepts and our relation to the plants, our attitude to the plants. Most of the people, even the scientists who are working with the plants, they don't feel that this is a big potential, you know, which could be exploited. And I believe that the future agriculture will consider completely a new concepts of communication, of dealing with the plants, because up to date, we as an end user, let's say, controlling the plant productions, but which is against the nature, you know. Now, if we are talking about ecology, about pollution, climate change, all these things would be solved. This is what I'm saying. All these problems which we have with the nature will be solved if we allow the nature to control itself, you know, autonomously. We are looking for autonomy, a system which allow them to control their environment. So imagine that if the plants in the greenhouse, because with the big respect, I'm doing that. I published, for example, this year, 11 publications on which lights intensity and quality the LEDs in the greenhouse on different type of plants, which one is the best. Unfortunately, I'm giving the literature what they need and the journals. Okay, I found that the combination of blue and LED in this and this person is the best for the cucumber, which is not true. I'm saying this frankly. The true, if you just change, you know, the cultivar, which will be another type of response. If you will do the same experiments in other geographical place, it will be another results. So why we don't go in this direction, that the plants themselves, based on this optimizing the photosynthesis process or maximizing, I'm not against that. I would like to have a tomato with 1.5 kilogram. Okay, you can have it if you wish. You put your machinery, your biological feedback system on the maximum production of photosynthesis, not the optimum. Okay, do it. But allow the plants to do it by themselves. Then we will save the energy. It will be, you know, very cost effective, because what we are doing now in all greenhouses around the world, the whole, turning the lights, you know, at 6 o'clock and turning off at 8 o'clock. And every farmer or gardener think that this is the best light quality and the best light intensity. So I'm asking these people, did you ask the plants what they need? And this is the time to ask the plants, to hear their answer. And this is the future research. Imagine if we would like to cultivate plants, which is one of the projects of Elon Musk and the other people on Mars. Do you know how much 1 gram, you know, costs, you know, sending to the above the gravity? I was in NASA and they informed me $27,000 US, 1 gram. Okay, so what we'd like to send? A greenhouse there, plants, a lot of water. The 1 milliliter of the water will be a cost of thousands there. So once the plants, if we would like to allow them to control their environment, they will use this, you know, water, light, whatever of another type of requirements efficiently. then there is a big chance that we cultivate these plants on other plants as well. Yeah.
Thank you, Professor Kalaji. And I have a question for you. And I think that we have time. We have 4 minutes still left. And in your energetic balance, you mentioned photosynthesis, you mentioned fluorescence, you mentioned heat dissipation.
Yes.
And I think I am not an expert in this field. I think that photosynthesis and fluorescence can be easily measured, but what about the heat dissipation? Do you think that it is possible to measure? It does make sense to measure heat dissipation or calculating it in somehow?
Well, it's calculated, by the way, by this type of chlorophyll fluorescence measurements, but it's not measured directly, it's indirectly, it's calculated. Because there is an equation which is making a clear relation between the percentage of the chlorophyll fluorescence and the heat dissipation. So in the most cases, yes, we can, let's say, have an image about the amount of these heat dissipated energy. Yes, and then this is an expression on the other side as a mirror, as we said about the photosynthesis itself.
Okay, thank you, Professor Kalaji. And I think that there are no other questions. I want to check the box. No questions opened, and in the chat, no other questions. So I think that we can conclude this session, and I thank again, especially the speakers of today, Professor Kalaji and Dr. Lela, and the MDPI personnel, and Cedric in particular for his patience. Thank you, Cedric.
A few more words from my side. I would like to thank the chair and the speakers for their time and interesting contributions to this webinar. Also, a thank you to our attendees. I hope you found this webinar interesting. As a reminder, the recording of the webinar will be made available as soon as possible on the webinar's webpage, on the conference webpage. Please note that you will have to be logged into Sci Forum in order to view the recording. So I wish everyone a nice day, morning, evening, wherever you are in the world. Have a good start to the week and take care. Bye.
Thank you.
Bye. Thank you.
Thank you.
Thank
Goodbye.
you. Bye.
Bye. Bye. Have a nice day.